Hello again, my dear students. This is part number 4 in our first lecture for the solid-state electronics. If you remember, in the previous part, we terminate our part with the principal equation of Ohm's law, where we have concluded that the current density, or what's called J, is equals to the conductivity sigma multiplied by electrical field eta, as you can see from this definition. Herein, we have introduced some new parameters. For example, sigma, which is the conductivity, is equals to n, the number of electrons in the conduction band, multiplied by the constant E square. E is the charge of the electron, 1.6 times 10 to the negative 19, multiplied by tau, where we define tau as the relaxation time, or the time between each two successive collision, over the effective mass m star. And also, one or two slides back, we also defined the term. Let me show it. The term mu, or the mobility, where we define the mobility as E times tau over m effect. And if you remember, in this part, I try to make it somehow logical for your understanding. When I say that whenever you become fatter, whenever you gain weight, then your mobility will be negatively affected. That's why the mobility and the effective mass are inversely proportional. So when the mass increases, this will reflect negatively on the mobility, so your mobility decreases, and this somehow makes sense. Now, before going to the last part of the lecture, we skip one important slide, which is this slide. If you remember, maybe in part number 3 or in part number 2, I'm not sure, we have defined what's called the EK diagram. And I told you in this section that the revision of this EK diagram is out of focus for this course because it needs some quantum background, especially quantum mechanics background and Schrodinger equation solving. However, we will deal with this EK diagram as this diagram represents the mathematical representation for the conduction band and the valency band, as you can see, where the conduction band is represented with this up parabola and the valency band is represented in the down parabola. And we also have noticed that we can estimate the effective mass of the particle using this EK diagram, and we already did an example where we have two graphs of the EK diagram for conduction band, and we estimate the effective mass of the electrons, relatively speaking, I mean, between graph number 1 and graph number 2. Now let's turn to a real example. As I mentioned earlier, this EK diagram can be mathematically driven through a sophisticated equations called Schrodinger equation, which is out focus of this course. And now we can make it by way of another, and then we can reach an EK diagram for any material. For example, let's see the EK diagram with or for the silicon material, for example, here. Oh yeah, this one. So as you can see, this is an EK diagram of a silicon material. This upper parabola represents the the conduction band. Then we have the energy cap, and then we have this down parabola, which represents the valency band. But as you can see that the slope here of this down parabola, or sorry, up parabola, somehow is different with respect to the slope here in this up in this down parabola. Here we have to return back to the concepts we have settled, if you remember, especially in this slide. When we say that free electrons are only defined in the conduction band and holes are only defined in the valency band. So whenever you are interested to know the effective mass of electrons, you have to search for the effective mass of electron in the conduction band, because free electrons are defined only in the conduction band. And whenever you need to know the effective mass of holes, then you have to search in the valency band, because holes are defined only in the valency band. So if we return to this slide, And I told you, please start to estimate the relation between the effective mass of the electrons and the effective mass of the hole. So you will tell me, okay, electrons are defined in the conduction band. Then whenever I need the effective mass of electron, I will search in this curve. And whenever I need the effective mass of holes, I will search in this curve. So this is simply the solution. Now let's start doing this exercise together while we are considering this curve. I will try now to plot the EK diagram of a silicon material. Okay, so let's now stop sharing the PowerPoint slides and go to our whiteboard. As you can see here, this is the conduction band abbreviated by CP, and this is the valency band abbreviated by VP, and of course this is the energy gap. So during this um, during this exercise, we are going to estimate the effective mass of electrons and holes. Let's start with the electron, and let's do the same exercise we did in part number 2. So what we are going to do is we know that the effective mass is inversely proportional to the second derivative of the EK diagram. So as we did in the previous example, first we determine the first derivative, then the second, then we say that 1 over the second derivative is the effective mass. And as we also did in our first exercise, we say that we simply can assume that this is a second order curve, which means that the first derivative of this second order curve is simply a straight line. So what we are going to do now is to plot a straight line like that, and then we say that okay, the effective mass, or not the effective mass, the second derivative is the slope of this straight line. So let's take a certain portion in the x direction, for example, from here to here. Okay, and then this is the slope. So the slope is simply delta E over delta K. This is simply the slope. Using the same method, we can also estimate the effective mass or the slope of the down curve, which represents the holes, because this is the valency band. So what we are going to do is that we will going to plot here a straight line like that. And then to make it easy, we will take the same x portion. So I will just extend the lines here. And we have something like that. Okay. So as you can see here, we have these two regions. Okay. As you can see, by comparison, the upper distance here is greater than the distance here, which means that the slope in the upper curve, slope of the electron, is greater than the slope of hole. The slope here of the electron is greater than the slope of the hole curve. The slope of the electron curve is greater than the slope of the hole's curve, which means that the effective mass is 1 over. So that means that the effective mass of holes is greater than the effective mass of electrons. This piece of information, my dear students, is a very important and a very principal piece of information in the electronics industry. And maybe later on, when we proceed with the bipolar junction transistors and the MOSFET transistors, we know that this information will significantly affect the design and the operation of MOSFET and the BGT. So by doing this exercise, we have concluded that the effective mass of holes is greater than the effective mass of electrons. So now the question, what is the impact of this knowledge or of this information? Now we have proved that the effective mass of holes is greater, but how this should reflect on? Let's go back to our slide. Okay, now you can see my slides, my dear students. So let me open the razor out again. Okay, so perfect. So as we concluded that the effective mass of holes is greater than the effective mass of electrons. So now the effect of the effective mass can appear in this equation. We just say that the holes are fatter than the electron. The hole's effective mass is greater than the electron effective mass. Automatically, that means that the mobility of holes will be less than the mobility of electrons. Again, this is a very fundamental and a basic information in your electronics study that will affect your perspective in designing transistors. Maybe until you reach year 4 in the VLSI courses, you will use this information that electron mobility is higher than the hole's mobility. Okay, so now we turn to the second question. If you remember, in the last part of the first lecture, or sorry, in the last part of in part number 3, I said to you that our next target is to go more deeply toward what is N. In this equation, let me remind you, when we start to say J, or when we start to calculate the current density, we say that this current density is simply the total charge multiplied by the velocity. The velocity comes from the d by dt component, if you remember, and this is the total charge, which is the single charge value E multiplied by the number of free charge, which is N. Again, here N is defined as, okay, N is defined as the number of electrons in the conduction band. So how shall we calculate N? This is the next biggest research. How should we know the number of electrons in the conduction band? Okay. In order to know the number of electrons in the conduction band, you have to know two basic information. Here, if we start the process from the beginning, what makes this electron transfer from the valency band to the conduction band is the thermal energy. So the thermal energy is the reason for the existence of an electron. So that's perfect. In order to make this example more clear for you, I will try to make it in a very simple manner. I hope I can do it. So let's now turn to the whiteboard. Okay. Let me make it in this way. If I told you, now imagine that you are in outside building A in our campus. So this is building A. This is the entrance. And okay, this is building A. And now you are sitting here. You are outside the building A. Here, you are here. Okay. And in your position, I told you, please try to estimate the number of students who are now sitting in room, for example, 311 in the third floor in building A. Try to estimate this number. If you try to solve this prediction problem, you would say that, okay, in order to know the number of students in this room, I'm not in the room actually, I have to gather some information. Part of this information is what is the number of available seats. Because simply, if this question is related to a lecture hall, for example, then you should expect a large number. If it's a small classroom, then another set. If it's a medium classroom like 20ECE, for example, then it's another set. So the number of seats will give you the range. You can make your estimation. For example, if it's a 50 seats classroom, then logically the number of students will vary from 0 to 50. Okay, so this is the number of seats. This is the first information you need to know before proceeding to estimate the number. What is the second information? Actually, the second is not an information. The second is a probability. What do I mean by probability? For example, if I ask you this question on Friday, 9 a.m. morning, your answer will be 0. Friday is a day off. No students will be on campus. But if I ask you the same question on Monday at 11 a.m., for example, okay, here you can say, okay, so maybe 75% of the room is fulfilled, for example. If I ask you the same question, but on Thursday at 2 p.m., you will say, okay, it's now Thursday, one day before the weekend, most probably not, the attendance level is not so high, so maybe it's only 20 or 30%. Please take care of that. In the 3 slots I choose on Friday, Monday, and Thursday, in the 3 slots, the number of seats is constant, but the difference is in the probability. So you can simply say that the total number of students is simply the multiplication of the number of seats and the probability to find the students. So on Friday morning, the number of seats is 50, but the probability to find the students is 0, so the output is 0. On Monday morning, still the 50 exists, the number of seats. However, the probability to find the students is higher, maybe 70, 80%, whatever. So this is how we will calculate the number of electrons in the conduction band. Electrons, okay, let me now return back to the slide. Okay, so electrons, in order to move from the valency band to the conduction band, they should be available places for the electron to set in the conduction band. If you remember the band theory lecture or the band theory demonstrative video, you know that this conduction band consists of a set of energy level, each we call it conduction level. So there is a places where the electron can set. So we need to know the number of places. This is the first issue. And then we need to think about the probability that this electron will move from the valency band to the conduction band. Okay, let's start with the second. Okay, let's consider the number of seats is a constant number. Okay, so we know it's by way or another that we have n seats, or not n, well, we will use n, so we will have n plus seats or whatever, any sample. So we have a constant number of seats. This is not an issue. Let's now think about the probability. And in order to understand the probability, actually, we need to think about the word I said in part number 3, maybe, where I told you that at 0 Kelvin, semiconductor materials will behave like an insulator. The 0 Kelvin condition is a Friday condition. I mean, now at 0 Kelvin, The conduction band still have seats. The classroom have the seats. But there is no probability to have electrons because the temperature simply is equal to 0. Again, this is the Friday example. You have the seats in the classroom, but you don't have students because they are. At 0 Kelvin, you have the conduction band. The conduction band includes seats, but there is no energy for the electron to move. This is at 0 Kelvin. When the temperature starts to increase, then the electrons will have more probability to flow from the conduction band to the valency band. Oh, I'm sorry, from the valency band to the conduction band. Because the source of energy, which is the thermal energy, will start to exist and will start to appear, so electrons can now move, knowing that we can fulfill the conditions of 3/2kT is greater than E. Okay, so now we can understand that the probability function is related somehow with the temperature. The probability function we are searching for is function in temperature. And it's only also function in energy. Why it's a function in energy? Let's say. Okay, let me now turn the color of the band, for example, to blue. Okay. Now, if I told you which is more difficult, to find an electron here, let's call this state number 1, or to find an electron here, let's call this state number 2. Please remember that this y-axis represent energy. So, in order to have electron in state number 1, then you have to have an energy which can move the electrons this distance. But in order to have an electron here in state number 2, then you should have an energy that makes electron jump to this distance. So the farther, the more difficult state. It's easy for you to jump this distance, but it's much difficult for you to jump to the other distance, to state number 2. So state number 1, the probability to find an electron in state number 1 is much higher than the probability to find an electron in state number 2. Okay, great. So what we are searching for is a function that is a probability function that is a function in both temperature and energy. Let's make life easy. Let's start with the easiest example. We are trying to plot this function at 0 Kelvin. So let's now start to plot. Let's say we are now seeking for 0 Kelvin case. Okay, I will keep the y-axis energy, and I will plot here the function that I'm searching for. I will call it f function. I know that this function is function in E and T. Okay, so now it's function in E and T. In the energy gap, in the energy level, we have two known points, which is the valency band and the conduction band. Okay. Now we are targeting to plot the function f in this state. Okay. As we see, or as we said, at 0 Kelvin, all the electrons should be in the conduction, in the valency band, because simply there is no reason, there is no energy that will make the electron jump from the valency band to the conduction band. So, as you are good students in probability, you can easily say that, okay, then the probability to find an electron in the valency band is equals to 1 while the probability to find an electron in the conduction band is equal to 0. Very simple. Here, mathematicians will be not so happy because in order to have a probability density function, or what we call the PDF, this probability density function should be continuous. This, as you can see, is not a continuous function because it's only defined here and there, but not defined in between. So we have to have it, or we have to make it somehow continuous. So I will make something which is not so good for you, that I will make it live. Okay, so here the probability is still 1, here the probability is 0, and then I make this connection in order to make the function continuous. This is when the temperature is 0 Kelvin. What if we increase the temperature a bit? For example, what if we reach the room temperature at 300 Kelvin? Then we should expect that some electrons will move from the valency band to the conduction band. Accordingly, you will have something like so. Now, the probability to find an electron in the valency band no longer 1 all over the time. It's now, to some extent, it's smaller than 1. And the probability to find holes, electrons in the conduction band is now slightly greater than 0 because some electrons jump from the valency band to the conduction. This function, we call it that Fermi-Dirac function. This is the Fermi-Dirac function. The Fermi-Dirac function is a function that represents the probability to find an electron, either in the valency band or in the conduction band. And it's a main function in both temperature and energy as we described. So, back to our presentation. This is the Fermi-Dirac function. As you can see, f of e here, let me use my pointer. F of e here is a probability, or the Fermi-Dirac function, and E is the energy, and this is the intermediate level. We will call it Fermi level. This level, we will call it Fermi level. I mean the level in between. So let me now make it also for you on my white paper. This level, this intermediate level, we'll call it Fermi level. So Fermi level is simply, as you can see here, a level in between, or in the middle of the energy gap between the conduction band and the valency band. This level is the level at which the function will turn from 0 to 1 at 0 Kelvin. And of course here, if you examine this point, you will find that at any temperature, the f of e here at the Fermi level will equal to half. I mean, the probability to find an electron is equal to half. This is actually somehow very confusing theory. Why it's a very confusing theory? Because based on our definition and according to our previous knowledge, electrons occupy discrete energy levels. These discrete energy levels is, for example, levels in the conduction band or the valency band or whatever. But it's impossible to find an electron in that energy gap. That's why in some textbooks they are called the forbidden gap, because there is no way, there is no available places to find an electron in the conduction in the forbidden gap, in this gap between EC and EV. So how you say that no electron exists in the forbidden gap or in the energy gap, but in the same way you say the probability to find an electron in the Fermi level, which is in the forbidden gap, is equal to how much? This is very confusing. Okay, in order to solve this confusion, let's now return to this slide. The guy standing outside building A and try to estimate the number of students in a room. Okay, in order to have an output here, which is a total, you should have seats and probability. For example, the Friday example when I said to you, no students will be in the campus, so the probability to find an student is equal to 0, that's why the output is equal to 0. Okay, that makes sense. But what if you have a probability, but the number of seats is equal to 0? Then the output will also equal to 0. For example, if I told you what are the probability to find an student, sorry, what is the total number of students in room, for example, 403. Now there is a student on campus. Today there is a student on campus, so there is a probability to find a student, but there is no seats because there is no room called 403. So you have a probability, but you don't have seats. So the overall or the output will be simply 0. This is here what we have now. We say that the probability to find an electron here in the Fermi level is equal to half, but the number of seats is equal to 0. So simply, that means that the total number of electrons at the Fermi level is equal to 0. We just make this definition to satisfy the mathematical condition, to have a continuous function representing the probability density function. But physically, this region in the Fermi in the forbidden gap or the energy gap will be multiplied by 0, then it has no effect on the data. That's why we have, or we keep it as a forbidden gap in the semiconductor material. So simply, this is the equation, or sorry, this is a graph. The blue curve represents the 0 Kelvin. Then, by increasing the temperature, the number of electrons in the conduction band starts to increase. As you can see here, for example, the red curve indicates higher temperature than the green curve. Because as you can see here, the probability to find an electron in the conduction band in the red curve is greater. That's why the temperature is higher. Mathematically, we can write this Fermi-Dirac distribution function in this manner. This is one of the equations that you should know it in deep. This equation, as you can see, is function in energy and in function is temperature, and K, as we previously mentioned, is the Boltzmann constant. So, of course, I believe that part of your tutorial problem will be toward substituting this equation. So, for any energy, you just need to substitute the term E minus EF at any certain temperature, then you can get the probability. Of course, this F of E is a probability, so all the time this will range between 0 and 1, not lower than 0, not higher than 1, because simply it is a probability. For example, you can make some home exercise. Maybe one of the exercise that I will approach for you is actually a bonus exercise that you can, for example, use MATLAB or any programming language in order to plot this equation and to show us these curves. You just need to change the temperature and then start to substitute an equation and do this exercise. This is very important. By the way, maybe one of the notes that you will tackle during the tutorial is a tricky note regarding the parameter K. K, the unit of K is very important in our course because if you remember, I told you that we will use usually the term E or the energy in the unit electron volt. So if you are using K, then you have to choose a K with a unit electron volt. Otherwise, if you pick up a K with a unit joule, then you have to transfer back this energy to joule. So you have to match the units between the energy and the K constant. Both should have the same unit, either both in electron volt or either both in joule. Now, we did 50% of our task because if you remember back to that example, when we talk about the number of students in a room, I told you that in order to estimate the number of students, which is in our case the number of electrons, you have to define two functions. The first one is the probability to find a student or the probability to find an electron, and the second one is the number of seats or the number of available places or seats for the electron. Now we define the first one, which is the probability to find electron. What about the second function? What about the the number of seats, or what we will call it the number of states, or what we will call the density function, or is that here just an infograph that indicate the Fermi level distribution with versus to F, and now this is what we call the density of states. This density of states represents simply the number of available places. We here define two density of states, one in the conduction band and the other in the valency band. The conduction band one is the one interested for electrons, because again electrons is defined in the conduction band, and the one here, the one in the valency band, is the one interested for holes. Again, if you remember, no seats are available in the forbidden gap. So simply, when you will multiply these two functions together, this is what we are going to do, then you will get 0 in this area, the forbidden gap area, because the number of seats is equal to 0. So now, in order to make easy, let me also told you a very important note here, that these equations again is one of the output of the quantum model, which is again out of focus for this course. So you are not requested to memorize this equation. If we need this equation in the final exam or in class test or in any type of assessment, then we will input you this equation as a given. You don't need to memorize it. It's a given equation. So this equation represents the density of state in the conduction band and density of state in the valency band. Let me now say something important. Now we are talking, or principally from the beginning of this part, we are talking about N, where N is the number of electrons in the conduction band. But we also have holes. If you remember this example, we also have holes. We will call holes, or the number of holes, P. Again, holes is defined only in the valency band. But simply, if you can take a screenshot and if you can think about it, you will say that, okay, this is very simple. N is equal to P, because in order to have an electron in the conduction band, that simply means that you broke a bond in the valency band and then you have a hole. So N and P are equal. N is defined in the conduction band and P is defined in the valency band. Okay, that's correct. But this is correct so far. Maybe 2 or 3 lectures from now, we will know that this is not correct all the time. But for the time being, please consider that the number of electrons in the conduction band, which is N, is equal to the number of holes in the valency band, which is equal to P. So N and P are equal so far. Now, let's turn to, we have now the two equations. We know the probability, and also we know the number of states, number of seats. Number of states are given. The probability, we go to some extent deeply, we understand to some extent why it's a probability, how it's changed with temperature and all these. So very simple, returning back to our original example, what you just need to do is to multiply these two functions together. If you multiply these two functions together, you will get the total number of electrons. But please remember that the number of the electrons is only defined in the conduction band. So in order to calculate the electrons, we will make the following. I will say the following. N, which is the number of electrons, is simply the multiplication of two functions. The first function is the states function, which is G of E. Again, this term G of E, but I will make it with subscript C to indicate that this is the conduction band. So GC of E is the big rule given in the lecture, in the slides I just showed to you, and multiplied by F of E, where F of E is the probability to find an electron. That's great. But again, electrons are only defined in the conduction band. So I have to make this limitation. I should calculate n only on the conduction band, not everywhere. So I have to make it in an integration form from EC to infinity. This indicates the integration with respect to energy of force, that I only define electron in the conduction band. Right? What about P? What about the number of holes? Okay, you will tell me that. Okay, number of holes are defined as the broken bond in the valency band. Great. Then we have to use the density of states, or the number of seats in the valency band, which is G V of E. Again, V here represents the valency band, multiplied by the probability to find a hole. Can we use F of E? No, we can't, because F of E represents the probability to find an electron. But here, we are not searching for an electron. We are searching for hole. So, how we can find hole? How we can find a probability to find a hole? So actually, very, 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 very simple. Let me, for a while, return back to my slides. Okay, as you can see here, in the valency band, in the blue area down, if F of E is the probability to find an electron, what is the probability to find a hole? Actually, very simple. If you are in the valency band and you couldn't find an electron, then by default, it's a broken bond and it's hole. This is like the red circle I'm plotting in the valency band, which represents a broken bond. So, very simple. The probability to find a hole in the valency band is 1 minus the probability to find an electron. And again, we have to limit this definition only to the valency band. So we will make the integration from negative infinity to EV dE. This what I call the integral form to determine the number of electrons and number of holes. 1 or 2 years ago, I think, in one of my unseen exam, final exam questions, I told my students that please write the integral form to calculate the N and B. Some students raise their hands on, there is something wrong. We don't memorize G of E or F of E. We don't memorize these formulas. I don't need you to memorize the formulas. You can just make it in this very symbolic way. And please note that most of the mark, the major part of the mark is on the integration limit, because the integration limits simply reflect your understanding. If you write n equals G of E times F of E, this is not correct, because now you are defining number of electrons everywhere. However, electrons are only defined in the conduction band, and holes are only defined in the valency band. So this is the integration. This is the integration form, or the integral form, for the number of electrons and number of holes. Now, let's now return back to the slides. Okay, so now we define the Fermi energy, or the Fermi Dirac distribution. We also define the density of the states. Now we can multiply these two functions together. Here, this is a graphical multiplication, one of the ways, I'm sorry. Back to presentation. Okay, this is one of the ways I usually use to make it simple. For example, let's use the green curves, which represent the electrons. So this green curve represents the seats of the electron in the conduction band, are multiplied by F of E, which is the probability to find an electron. Then I get the number of electrons in the conduction band. This is green area. What about holes? I use the number of states in the valency band, which is the red curve, multiplied by the 1 minus f of e, which is the probability to find a hole. Then this is that red portion, or the red peak here represents the number of holes. So this is a graphical representation. Also, you can make it. This is very simple. You don't need to memorize anything. You can just reflect what you understand in this graph. Okay, regarding the mathematical part, as I mentioned, you don't need to make it by your hand, but this is simply the integration. In order to calculate the number of electrons, as I just mentioned, what you have to do is very simple, to multiply the g of e times the f of e from EC to infinity. This is the formula for g of e, and this is the formula for f of e. You don't need to make it by hand. If you wish, so please do. Don't worry, but you are not requested to make it. So you will get, by the end of the day, you will get the final form of n. This is the final form of n. Again, you are not requested to memorize this final form of n. This is the output of the integration, or the output of the integration, again, yes, between f of e and g of e. Very simple way and very simple manner you can make it in this way. So this is the first equation, and to make this equation somehow simple, we get this complicated term, and we call it NC, or the effective density of states in the conduction band, so that N equals NC e power EF minus EC over KT. So we can put the equation in a better, simple mathematical way. Again, you are not requested to make these derivations. However, we will use a final form in solving equations, by the way. Okay, so what about holes? Again, the same issue. What I'm going to do is to integrate from negative infinity to EV, G of E, 1 minus f of E dE. This is a very simple form, as I mentioned. Then you will get the output in the same manner, where we will divide this big term as an NV, or the effective density of states in the valency band, where P equal NV E mar minus EC minus EF over KT. Okay, so now this is the end of our first lecture. It's a long lecture, a lot of mathematics, a lot of conceptual issues, a lot of maybe a lot of revision somehow. So I hope that you feel engaged to the lecture. Maybe after this first lecture, you recognize that we are dealing with somehow a physical, mathematical tough course with some concepts of mathematics. We will, again, as I mentioned in my zero lecture, we will do our best to make life easy for you. You will have the opportunity to see this videos millions of times using the YouTube platform. We will be available everywhere, online and on campus, in order to offer you help. So don't worry, don't hesitate to contact us. We will have a regular follow-up meeting instead of the lectures and the tutorials, or in addition to the lectures and tutorials, actually, in order to make life more easy and more clear for you. Thank you for this first lecture. See you in the next lecture, where we are talking about what's called the mass action law. Thank you very much, my dear students.